Hello guys, welcome back to my channel Memo African Motives. Still working on engineering science N4. So in this platform we shall be working on the question which is an application of angular motion. That is from the question paper which was written in February 2022. So I actually chose this question paper there so that we can note a lot of errors which were done there on the memo there, so that we can actually correct one or two things there. All right, we are given the question which is on question number 3 that you're going to focus on. So if you're new guys, you can consider subscribing so that you become part of the family Memo African Motives. So let us quickly rush through the question that you're given on question 3, that is angular motion. We are given that a turbine in an electrical plant has a diameter of 6.5 meters and is rotating at 750 revs per second. Take note guys, this is in revs per second. Okay, the turbine slows down to 500 revs per second again in 45 seconds. Okay, so the question is to determine the angular deceleration of the turbine. Okay, let's just list down our information where actually the first error occurred. We are given the diameter, so we are going to just take our diameter, which is 6.5 meters. And normally whenever you have a diameter, you must think of the radius. So it's wise for you to just calculate the radius. Okay, where we know that radius is diameter over 2. So that's 6.5 over 2 there, which is going to give you 3.25 from your calculator, which is in meters. Okay, then we are given that it is rotating at, so which means we can obtain the angular velocity from the number of revs per second that we are given. So we can obtain the initial angular velocity, which is omega 1 in this case. And we know that omega 1 which is the angular velocity, is equivalent to 2 pi times, if this was like this guys, if it was revs per minute like this, you are going to multiply by the revs per minute that you are given over 60, so that it will be in revs per second. But in this case, it's already in revs per second. So you're just going to multiply by the revs per second as they are. Dividing by 60 is a sign of converting to revs per second. So that is wrong if you divide this again by 60, because already we are given this in revs per second. So you're not going to divide, but you're just going to multiply there. Okay, so take note about this guys. So you multiply direct by 750 there. Okay, so this is going to give us 1500 pi rads per second. Remember, this will be in rads per second. Then it decreased because it's now slowing down to 500. So still the same thing. That's 2 pi times 500, because it's already in revs per second. Okay, so you are not dividing by anything there. So this is going to give you 1000 pi rad per second. So you can write it as a decimal, or you can just put it in terms of pi. Okay, it's one and the same thing. Then the time, it's 45 seconds. So you're given also the time, which is 45 seconds. The time, there's nothing that we can do there. Just write it like that. Okay, so the first question is to calculate 3.11, the angular deceleration of the turbine. Okay, which we know that deceleration or angular acceleration is taken from this symbol here, alpha, this one, which is alpha, to represent the angular deceleration or acceleration, which is the change in angular velocity over the time taken. So it's actually the change in angular velocity. So the change, it's omega 2 minus 1 over the time that was taken. So it's actually change in angular velocity. If you watch the video on the introduction, you will see that this part. Okay, change in angular velocity. All right, that's what you have over the time taken. So this T is the time taken. Oh, so just substitute here. So this is also measured in rad per square second. All right, so the omega 2 which is the one that we corrected there, is the one that you're going to substitute, not the other way, this one. So it's got 1000 pi there. So that's 1000 pi minus omega 1, which is 1500 pi. So it's going to be 1500 pi like this. Everything over the time which was taken, and our time is 45 seconds. So that's 45 there, which means you are going to obtain a negative there, because actually it was reducing in terms of speed, so definitely it's going to be a negative. So this one will be negative 34,90658, whatever that you're going to have there. So you can round off to 3 decimal places, which is going to give you negative 34,907. This one is going to change into 7, which is rad per square second. So that's what you're going to have in this case. It's going to be a negative, just like when you are working with the linear, when the speed or the velocity reduces, you know that the acceleration is what is a negative. So that is the same thing even on angular deceleration or acceleration. Okay, then on 3.12, calculate the number of revolutions completed during the deceleration. Okay, the number of revolutions. Okay, we know that in order for you to actually find the number of revolutions, this is the concept here. What can I say? Okay, the number of revolutions, let's just say number of revolutions is equal to, this is equivalent to the theta. Okay, let's just say theta over 2 pi. Yeah, now it can make sense, because in one revolution we have got 2 pi radians. This is equivalent to 1 revolution. So which means to find number of revolutions for the pi radians that you're given, you're going to divide the angular displacement. So let's just say this is angular displacement, because that's our theta there, that's our angular displacement, over 2 pi. So 2 pi represents 1 complete revolution. That's 1 revolution. It's a complete revolution. So that's why you have to divide the angular displacement, because this one is measured in rads there, and this 2 pi is also in rads. So that will give us the number of revolutions. Okay, so that means we have to find the angular displacement first, which is theta, that angular displacement. So where can we have our angular displacement? Okay, there are so many formulas that you can use to find angular displacement, but as for me, I favor this one. That's omega 1 plus omega 2 over 2 times the time which was taken. You can actually use this one, but there are so many, guys. There's also this one, theta is equivalent to, that's omega 1t minus half, that's alpha t squared. Yeah, something like that. So there are so many. So using this one, you're going to have theta, which is the angular displacement. That's omega 1, omega 2, the ones that we are given. We just substitute, because these ones we have them. That's 1500 plus 1000 pi. So that's 1500 pi plus, we are adding this time, plus 1000 pi over 2. Okay, so this is going to multiply to the time which was taken, which is 45 seconds, like this. Okay, so definitely we are going to obtain a theta there. In this case, I obtained something like 56250 pi. This is what you're going to obtain in radians. But we are saying that for each and every part that we have, in order for you now to have the number of revolutions, because we need to find the number of revolutions, so it's going to be theta, which is the angular displacement, over 2 pi. So you have got the angular displacement, this one. So therefore, number of revolutions in this case is going to be 56250 pi. This is our theta over 2 pi. All right, so this is going to give us something like 218. Yeah, this is so many, 281. All right, that's 28125. okay, revs. So this is what you're going to have, guys. Okay, so take note, guys, you answer the question in exam according to how you are asked the question. If it was revs per minute, therefore you're going to divide by 60 these values that we are given. But according to this question, this was revs per second, so we answer this according to what we're given. So we do not correct ourselves in exam to say this is going to be revs per minute. No, we answer the question according to how it is displayed in exam. So that is how it was displayed, and that is how we were supposed to answer this. I'll come out with another question working on this same type of a question, but now it will be like revs per minute, so that you can actually see the difference of what I'm talking about there. Okay, on 3.2, this one was also a direct question that we are given. We are given that a body with a mass of 500 kgs is lifted by a winch with a drum diameter of, we are given. Okay, so this is actually a board that is going upwards, and as you can see that if something, guys, is actually going upwards, there is going to be the gravitational acceleration there. So we are going to talk about it again. So we've got the mass. Anyways, let's just take our mass, which is 500 kgs, and let's just put our information in order here. And the drum diameter, the diameter is 300 millimeters. Conversion of units is very, very important, guys. These are millimeters, you have to convert them to meters. You divide by 1000. This is going to give you 0.3, which is in meters. So likewise, it's very important for you to also have the radius again. So you're going to divide 0.3 divided by 2, like I did last time. So this is going to give you 0.15 meters as the radius. So you just put it, both of them. You never know, you might need it. The body is lifted vertically upwards over a distance. So you're given the distance, which is actually the height, or just as, or you can just put as the height. I don't know the way that you like putting this way, so you can just put it as s, or the height, and it accelerates at a rate of, which means you're also given the acceleration of 1.3 meters per square second. So this is the concept, guys, that is happening here. We have got gravitational acceleration, and this is going up like this because it's being taken upwards. So you've got acceleration and also gravitational acceleration. Whenever you are going upwards, the concept is you're going to add the two, the gravitational acceleration to the acceleration that you have here. So that is the concept, guys, because remember your gravitational acceleration, that's 9.8 meters per square second. So these will add together because they are going upwards. If it is going downwards, you subtract one to the other there, but this time you add. Okay, so what is the question, guys? The question is calculate the work done to lift the body. Okay, so what is the work done there on 3.21? All right, that is 3.21. So we know, guys, that the work done, which is can be written as W or WD like that, is actually equivalent to the force times the perpendicular distance. We talked about this. So this is the perpendicular distance, which is actually the radius. Okay, then this is the force, and we know that the force is actually equivalent to mass times acceleration on a steady state when you are just moving, maybe in a horizontal manner like this. Okay, you've got a body of mass, a certain mass, so the force is going to be mass times what? Acceleration. But this one, because it's lifted upwards like this, there is going to be another acceleration, which is the gravitational acceleration. So in place of this acceleration, we shall have actually two things. Like I said, that you are going to add them together like this. So that means our force is going to be mass times the acceleration, which is added together. That's G plus A. So it's going to be G plus A like this. So that will be our force, guys. Okay, so don't freak out, guys. This is just the force, but we say the work done, it's force times the distance. So therefore I'm going to write this as work done, it's force, which is this force. This is our force here, which is mass times the acceleration. So this is combined acceleration, okay, times the distance, which is times the distance, which is the radius. So you can just write like R, or you can just write as S, no matter the way that you want to put it. So we can actually substitute, guys, from the information that we are given here. This is our information. The mass, we have got the mass here, so the work done is going to be the mass of 500 times the g, because we've got g there, which is 9.8, and the acceleration of 1,3, so it's 9,8 plus 1,3, like this. So that's what you're going to have in this case, times the radius, which is the perpendicular distance. That's the radius, which is 0,15. You use the radius there. So this is going to give us something like 19425 joules, like this. Okay, so you can actually put this in joules, or you can put it to kilo. Remember, kilojoules, that's 3 digits after the comma, so it's going to be 19,425. That will be kilojoules, like this. So that will be your work done, guys. That's what we have, guys, on 3.21, not 3.31. So it's all about the information first. Once the information, always try by all means to list the data down, or the information down. Then using the information, we can be able to answer any question. It will be very, very easier that way, rather than to just rush through the question. No, write down the information. Okay, then determine the power required to lift the body, the cardboard. Okay, and we know that power, guys, is actually energy over the time taken. So this one is just pretty direct also, because we know this power is equivalent, this is 3.22. okay, is that so? Yeah, so power is equivalent to the work done over the time taken. So this is actually work done. All right, and we've got the time taken here, which is in seconds. So this can give us power in watts. All right, but where is the power? Where is the time? Because I looked around here, I didn't find anything that has to do with time. There's no time here. So guys, what are you going to do? All right, this is the concept here. Using this, the distance, the displacement, or the distance, whatever, the acceleration, what else do we have here? This is what we have. And the velocity, do we have any velocity? We do not have. Okay, let's just take these values down, because initially this is being pointed, it's going up, so we're not given, so initially it's at 0 there. This one is on a condition where our initial velocity is at 0. So let's just put this information. We want to calculate time. We are going back. I'm going to come back with this formula, because we can't use it for now without time. So our u said that's 0 meters per second. Our acceleration is 1,3 meters per square second, and the distance, the displacement, which is 3,5 meters. So this is the only information that we have, and we have to work miracles here to find time. All right, how can we work miracles here? Actually, these are linear. We know that from our linear, S is equivalent to ut plus half at squared. That's half at squared there. So you can actually take this, because this is gonna be out, because since our u is a 0 there, so it's gonna be taken out. So you're going to have something like this. S, which is 3,5, is equivalent to u, that's 0 times t. So 0 times t is actually 0, so there's nothing there. So you're going to be left with half of, let's just times here, the acceleration, which is 1,3 times t squared. Yes, we won. We actually won, yes. So which means we can actually win from this one. Okay, so what are we going to have? 3,5 is equal to half of this. You can actually multiply from your calculator, half times 1/2 times 1,3, which is going to give you something like what? 0,65. Is it 0,65, guys? Just cross check from your calculator there. All right, so that's 0,65 t squared. So, and I want to calculate t, so I can actually divide by 0,65 here. 0,65. Just play around with your calculator, guys. So that's t squared is equal to 3,5 over 0,65. So how can I find t? Introduce square root. All right, that's my t here, which is going to be 2,320, yeah, 47, something like that. So you can round off maybe to 3 decimal places, which is going to be 2,32. This 0 can, like this 4 cannot change. This 0, so it's going to be a 0, but there's no need of writing this. Okay, anyways, let's just write it. So that is our time here. So it's now very easier to apply our answer here. Power is equivalent to the work done. We got the work done before. Yes, we got this. It was 19 what. Let's see what we had. This was the work done here. It was 19,425 over the time. Now the one that we just calculated, the time is 2,320. Guys, there's no need of you writing this 0. Okay, so you can just use your calculator there. That is going to give us this decimal. Just imagine. Okay, let me just write it here. 8372 8448. Yeah, this is what I actually obtained here, and this is measured in watts. As you know that power is measured in watts, so you can actually round it off here, or you can put it maybe to kilowatts, because remember I said kilo from this, because it's going to be like this 3 digits here, which is this 3 digits after the comma, like this. So it's going to be 8,37. So this can actually round, since we are now having 3 digits after the comma, so 8 can change this 2 into 3, so it's going to be like this, which is in kilowatts. Yeah, makes sense. Now we can just put it in watts, like 8372,845 watts if you want to put it in watts. But guys, just look at the presentation. But anyways, it's one and the same thing actually. It's one and the same thing. Don't freak out, guys. Just one and the same thing. All right, so that's how they can ask these questions, as you can see, on angular motion. This is something which is very important in our syllabus, and to know all these concepts and revisions. So that's it, guys, from Memo African Motives, working on past papers and revisions for engineering science N4. Till we meet again.